This episode, I spoke to European Space Agency astrobiologist and deep space exploration scientist Nicol Caplin about the search for life beyond Earth and how the study of microorganisms will play a crucial part in the future of crewed spaceflight.
Hello, my name is Nicol Caplin. I'm a deep space exploration scientist at the European Space Agency based in Noordwijk in the Netherlands.
Fantastic. Well, thanks very much for joining me in the podcast, Nicol. It's great to have you on. I mean, you're an astrobiologist, but I have to say, deep space exploration scientist is way cooler. That has to be one of the coolest job titles I've ever heard.
Thank you. It sounds very glamorous, doesn't it? But what it essentially is exploration science that goes beyond low Earth orbit. So that's where the deep space part comes in.
Yeah.
And you mentioned astrobiology. A lot of people don't actually know what astrobiology actually is. They think it's anything to do with biology in space, but it's actually quite specific. Astrobiology is concerned with three main topics. That's the origins of life and where we came from, the limits of life and what it can withstand, and then the really exciting one, which is the possibility that there could be life elsewhere.
Yeah, and given that sort of deep space exploration aspect of your job title, presumably that means, and working for the European Space Agency, presumably that means you approach astrobiology from the sort of the space flight angle.
Yes, that's correct. So, in terms of the deep space side of astrobiology, what astrobiologists have traditionally done in European science is fly experiments in low Earth orbit to see how some extremophiles, and I can tell you a bit more about what an extremophile is in a moment, but how these samples respond to the spaceflight environment just in low Earth orbit. So that could be the vast temperature fluctuations, so going from very, very hot when things are directly in the sun to extreme cold temperatures, intense radiation environment, including galactic cosmic rays, and then, of course, microgravity and how life is responding to that. And then when we talk about doing astrobiology in deep space, well, for ESA, that means going a little bit beyond low Earth orbit. So outside of the Earth's magnetic field. So we get a lot of protection from all of the harsh radiation in space from this protective layer. And that's where the International Space Station sits within. So anything that we are doing on the International Space Station by default is protected by this lovely layer. But astrobiologists are really concerned with looking at what types of life could exist beyond low Earth orbit and outside of this layer. And one of the ways that we can do that is by going to lunar orbit.
Astrobiologists and in sort of exoplanet science, people always talk about life as we know it, finding life as we know it, and that sort of leads to people get excited when you find an exoplanet that is in the so-called Goldilocks zone, water can pool in the surface, because that's supposedly conducive to life as we know it existing. But as your sort of exploration and study shows, there are lots of organisms on Earth that don't even appear to exist under conditions that are conducive to life as we know it. Do you know what I mean? So, those so-called extremophiles, does that give you hope that we will find life on less seemingly habitable exoplanets or other bodies of the solar system, for example?
Personally, I think it's entirely plausible to think that there is life out there in the cosmos. But I also think that there is the possibility that that may not be the case. But I'm in the business of finding that out. So that's something that excites me. And I think we should continue looking until we see evidence not to look. So you mentioned extremophiles. Now, extremophiles are classed as organisms that you find that live beyond the realms of what is classed as habitable for you and I. For example, if you put us in a room and blasted us with a really, really high dose of radiation, well, we'd get poorly very quickly. But there are certain organisms and also plants and bacteria that can withstand high doses of radiation, way beyond what we can withstand, and also your pets at home can withstand. So and this is the type of life, not you and I, that we think could be out there.
Do you sort of hold out much hope for finding life of any kind in our solar system? I'm sort of specifically thinking of future missions to the icy moons around Jupiter.
Yes, so that's one of the places that astrobiologists want to focus on, because where you find water, you therefore could infer that life could exist. Water is the number one requirement for life as we know it. But in order to do that, you need to then test out what could actually be surviving in those conditions. So, for example, we have an experiment in the current planning called Ice Cold, and this specifically focuses on simulating the icy moon environment outside of the ISS. So it's an external payload, and what it will do is place biological samples outside in these simulated conditions. Now, if things can survive this, then that implies that going to the icy moons, sending probes there, looking for more examples of life, is a good line of inquiry. So we should go and do that.
I mean, you sort of also think of the Cassini mission, which was, studying part of its mission was to study the possibility of life existing in the subsurface ocean around the icy moon Enceladus. I mean, as far as I know, no signs of life were found. But do you think, for example, it's worth sending a similar mission back to the Saturnian system for a sort of follow-up, just to make sure?
I always think it's worth doing things more than once, and I think that speaks to all scientists. As technology develops, and it's developing at quite a rapid pace, instruments are becoming smarter, smaller, and we're sending more and more of these types of instruments to space all of the time. So as this technology progresses, then we may find life way beyond our own planet using more sensitive instruments. So I think it's a good and exciting thing to be part of.
One of the things I always love whenever I get the chance to speak to an astrobiologist, I always love asking them about the theory of panspermia, because it really intrigues me that might be a possibility. I was wondering if you could give us a bit of an overview of what that is and sort of how it might work and how likely it is.
Sure. So panspermia theory, in simple terms, is the theory that life could have been imported here from somewhere else in the cosmos, be it on a comet or another vessel. The idea is that it could have seeded life here on Earth, or some types of life here on Earth. So one of the ways we think that could have happened, possibly one of the theories, is that I've seen some really good illustrations where you've got little bacteria that are just hanging on to a rock flying through space, and that's kind of a very interesting and comical way of looking at it, but it's not entirely unfounded. But what's probably more likely is that something was buried beneath a layer on one of these comets or other body that protected it from not only the harsh space environment but also re-entry and the blistering temperatures that could have, or that would have been subjected to. So we can imagine that perhaps once upon a time there were some bacteria or archaea buried into the surface of a comet, with a few layers protecting it, kind of like a bit of a spacesuit, and then it peppered the Earth.
Is there a possibility that we human beings might have that human life might have arisen that way?
It is one of the theories that life didn't spontaneously begin on Earth, but it began somewhere else and was therefore imported. And there's kind of no proof of that, but we can test out these extremophiles and see if that is a plausible theory indeed.
It's incredible to think that maybe around the galaxy that's just happening everywhere, that life is just being transported around the galaxy, isn't it?
Yeah, so you can think too deeply about it and then it can be a little overwhelming if you think, oh gosh, there's all of this life exploding around the galaxy or beyond, who knows, and somehow it traveled here. But it's exciting.
It certainly is. It's definitely worth talking about some of the projects that you're involved in, because I've been reading up on some of the projects that you're involved in, and they're just absolutely mind blowing. I mean, the one that really got me excited and interested was Biorock. Could you tell us a bit about that?
So yes, Biorock is fantastic. I describe it as the world's first miniaturized biomining facility to go to space. Now, what Biorock did was test samples of bacteria that are known to be used in biomining processes, which is an already established process on Earth. We can extract precious metals and materials from Earth, such as copper or gold, from rock, using these large-scale industrial processes with bacteria to extract those materials. But there's this thought that, well, we could do this off Earth, because if there's this vision, and there is this vision of colonizing the moon or Mars or beyond, then not only is it very economically costly to be taking materials with us, but also environmentally, we don't want to be depleting our precious planet of finite materials and resources already. So there is this vision to carry out these practices on the moon or Mars. Now, the way that we can do that, the way that we can test to see if that's really worth doing, is by exposing these bacterial species that are commonly used in these processes on Earth. And if they perform the same or better than they do on Earth, then why couldn't we use them to carry out biomining off planet? And the results so far are showing some really promising things. These bacteria don't seem to be struggling with the microgravity. And we already know that some of these bacterial species that have specifically been chosen are resistant already to radiation. So then you have this beautiful combination of a very resistant bacterial species that can also survive these space conditions in microgravity. And there you go. You might be able to mine off planet someday with them.
So what would they actually be able to do? How would it actually benefit the crewed mission on the moon? Is it sort of like building materials, or?
So it would be things used within building materials, but also other uses for precious metals. We're focusing specifically on the metals. There is also great work going on with building materials, using the surface of the moon, lunar regolith, to construct bricks, for example, using additive manufacturing, 3D printing. But for taking the precious metals and making wiring and cabling and all of that sort of thing, and the structure themselves, the metals, then that's the thought, that we could use these metals for incorporating them into construction.
It also, I mean, I could be wrong, but it also sounds like it would be less sort of destructive and invasive than diggers, digging chunks out of the lunar surface. Is that the case, or am I just being optimistic?
I'm not sure if it's less invasive in terms of extraction is extraction. Whichever way you do it, you're going to be taking something away. But taking crews to the moon and working in that lunar gravity environment. Well, I'm sure you've seen the videos from the Apollo missions and astronauts falling over and how tricky it can actually be working and adapting to work in that environment. So if we can just imagine some large-scale vats that are on the lunar surface that are placed there, and then regolith or basalt is added to these vats, and you just have bacteria in there in a closed system working away and then extracting the material through an outlet. It could be a lot more of it's just a more logical way of doing things than having to rely on clumsy astronauts.
I do love all the really cool experiments that go on in the ISS. I mean, I think maybe not everyone sort of is aware of just how much sort of scientific research goes on. Has the ISS been of real benefit to your own personal career and field? And also, would you ever love to go up to the ISS yourself and actually do your own research in zero gravity?
This is a brilliant question. The ISS has been a continual human presence in space for just over 20 years now. And for European science, that's been a key part of our research. Without the ISS being there, I wouldn't be working on the projects that I'm working on. So, of course, I'm going to say that the ISS is absolutely crucial to what I do. And would I go there myself in a heartbeat? I think, that would be an amazing opportunity. And not only do I then get to plan the experiments, I'd actually go and get to carry them out myself.
Yeah, because that's one of the things I think. Like, it isn't it sort of the case that scientists like yourself on the ground have to convey the procedure to the astronauts, and then they have to do it. Whereas if you were there, you could just do it yourself.
Yeah, it might sound a little bit control freak for me to say it that way. But part of my job is not only communicating the scientific requirements to the engineering teams to make sure that the hardware that gets developed will fulfill the scientific requirements, but also translating those requirements into operational speak so that our operational teams can communicate with the astronauts and make it absolutely crystal clear what needs to be done. Because, well, a lot of the time you only kind of get one shot. You load an experiment on a rocket, it goes to the ISS, it gets offloaded, and there you have it. It needs to be installed and carried out. And there's not much room for error in a lot of the cases.
Another experiment that I was going to hoping you would tell us about was the Biofilms experiment. That's another really, really interesting one.
So I already mentioned how useful bacteria can be. I'm very pro-bacteria for biomining, but they can also be a hindrance. I'm not sure if you've seen what the inside of the ISS looks like at the moment. I mentioned that it's been a continual source of human presence in space for the past 20 years. Well, there's no cleaning crews that go around an International Space Station. And so there is an issue now that there is some contamination signs showing on some of the walls. So what Biofilms seeks to do is to work out what new materials could be used on future spacecraft to enhance the level of cleanliness, to improve hygiene in areas where you're not going to be able to clean often. And so one of the ways that we can do that is by taking metals that have known antimicrobial properties on Earth, for example, copper, and exposing them, having bacteria cultured on the surfaces in the space environment to see if being in space actually makes a difference or not. Do they still retain these antimicrobial properties? Or do we need to apply some special surface treatments to them? Do we need to laser etch them? Is there something that the bacteria are doing in space, which means that they adhere well or less well to the surfaces in microgravity? And then we can take those results and then we can start building them into smarter surfaces for spaceflight. And one of the great things about doing that is that we're also, at the same time, developing these technologies that can be used on Earth. So they have immediate Earth benefits. So in areas that you need enhanced hygiene, I mean, look at us right now. We're in the middle of a pandemic. Cleanliness has never been more important. So if we can incorporate these smarter surfaces into places that people really need it, then that's only a good thing.
Absolutely. I mean, it also sounds like one of those ISS experiments that's sort of looking beyond the life of the ISS and, to sort of beyond Earth orbit and even maybe potentially to Mars. How are humans and the equipment going to survive, like, longer journeys where potential rescue is a lot farther away?
It's an important thing to consider if you're going to be on longer duration spaceflight missions, that you're going to need this hygienic environment. And so when developing future spacecraft, if we can incorporate these technologies and therefore improve the hygiene of new living quarters for astronauts, food preparation areas, toilet areas, then we can start to see a more sustainable presence out in space and just a nicer environment in general.
I suppose, that also brings us nicely onto yet another experiment that you're involved in, which is the Rotifer B experiment, because that sort of speaks to long duration spaceflight as well, doesn't it?
So Rotifer B looks at rotifers. Now, not everybody knows what rotifers are. Tardigrades are similar to rotifers, and you may have heard of tardigrades or water bears, but found in exactly the same environments that tardigrades are found in are rotifers. Now, these are these small swimming or crawling, depending on the species, microorganisms that are also incredibly radio resistant. And what the Rotifer B project is looking to do is use rotifers as a model for DNA damage and repair in space. Rotifers have this amazing capability to repair their own DNA. You can subject them to massive doses of radiation through proton beams or X-rays, and then they can just repair themselves. So near lethal doses that almost kill them, and then they can repair themselves. So we want to see if there's a difference between how they do this on Earth and how they do this in space, to see if there's a difference in how DNA actually repairs itself in space. And then we can extrapolate that data and do some omics research, and also see if it therefore can then be applied to humans.
Yeah, I think that's one of the things that I always wonder when we talk about studying extremophiles in space and how they survive, is how you would actually apply what you've learned to humans. Because it's not as if, well, I mean, I would imagine it's not as if we can easily replicate what's sort of going on and genetically in these extremophiles and how they adapt and survive in space.
No, but and at the same time, we can't take you and I, as I've explained previously, can't subject an astronaut to some huge doses of radiation and then kind of have a look at their DNA and see how that's repairing. No, they would die. So by doing that with the extremophiles, we can then learn what the mechanisms are, and then we can see, okay, do humans possess these similar mechanisms? Is there a way of engineering these mechanisms perhaps at some point in the future to humans? Could we repair our DNA at some point? So there's all of these open questions, but you have to start small, and extremophiles are the way to go.
I often wonder with someone like yourself who has studied extremophiles so much, do you ever sort of like almost despair at just sort of how weak and needy humans are?
We're really not well put together when compared to extremophiles, are we? Do I despair? No, I think there are some great qualities to being human, but I do get a little bit jealous of the extremophiles that can sometimes survive open space without a spacesuit. But if we went to space without a spacesuit, well, we've had it.
Absolutely. I mean, you mentioned tardigrades, they can go through all sorts of can't they sort of like dry out and like survive without water and all sorts of things like that?
Yes, and in the exact same way, rotifers can also dry out. So we can desiccate samples of tardigrades and rotifers, dry them down so they are almost completely dry. It's something like 99.8% dry matter, so just the tiniest bit of moisture in there. And then when they're in this state, we can then do all sorts of things. We can put them in very high temperatures. We can freeze them right down. We can irradiate them. We can put them in acid. And then once you take them out of that environment and you revive them by just rehydrating them, then they seem to carry on as normal. They are really, really tough things. But one of the common misconceptions with these particular extremophiles is that they can just survive anything and they don't have to go through that desiccation process. And that's completely false. If you plucked a tardigrade or rotifer out of your garden pond and you put it in some boiling water, it would die, because it just can't go through those shifts without going through that desiccated process.
Ah, right. Yeah, that's cool. Yeah, that's definitely worth clearing up. Yeah, because you do have this sort of impression of tardigrades, that they can just survive anything,
Well, and that's what caused a lot of concern. I don't know if you recall, a few years ago there was a mission, the Biorock mission that crash landed on the lunar surface, and that was containing a payload of tardigrades, and this caught the imagination of the media around the world, that there's these tardigrades that have crash landed on the moon, and this is of utmost concern because they survive anything and they're going to grow and replicate, and then maybe one day they'll take over the world. Well, this this isn't the case, because the tardigrades that were sent, again, are in this dry, desiccated state, and they can only be woken up with a rehydration. And well, there's no liquid water hanging about on the surface of the moon. And these samples were also encased in multiple layers of metal and resin. And if by some chance the all of these layers burst open when the lander crashed, and some water found itself onto these samples by some incredibly low chance, I don't know, a comet hit the moon, an icy comet, and then hydrated all of these samples, they wouldn't last long, because the radiation is what gets them.
Right, okay.
And also there's no food for them.
Yeah, absolutely.
They'd either get irradiated and die, or they'd starve to death. So it's not a nice fate for them. Just
talking about the moon actually brings me on to the next thing I want to ask you about, which is because you sort of mentioned previously about the limit of the ISS being in Earth orbit, and the sort of necessity, scientifically speaking, to go beyond. Because I understand that one of the future projects that you're involved in is the Lunar Gateway. I mean, it'd be really interesting to get an astrobiologist's perspective on the Lunar Gateway and the possibilities that's going to open up for scientific research.
Yes, so the Lunar Gateway will be another spacecraft similar to the ISS, but much smaller, and it will be placed in lunar orbit. Now, what's really interesting about the particular orbit that was chosen for this spacecraft is that it's a near rectilinear halo orbit. And what that means is it spends some of its time outside of the Earth's magnetic layer. So you will have this deep space environment where you can expose astrobiological samples without this protection. For the very first time, you can really expose these samples to deep space.
So what sort of possibilities does that open up then? And are you personally sort of planning experiments that are going to take advantage of that aspect of the mission?
So at the moment, it's very much in the planning phase. And we're having a look at utilisation for the first 15 years at least. And this spans across many, many disciplines, not just astrobiology, but also human research, technology, heliophysics, looking at lunar dust as well. So there's all of these research themes and topics. But for the astrobiology community, they're particularly concerned with finding out kind of the next stage of research, going that one phase deeper beyond low Earth orbit studies. I mean, low Earth orbit studies are very important, of course. We learn a lot from them. We can expose samples to the radiation and the space vacuum, all of the temperature fluctuations, and of course, microgravity. But you're still within that protective layer. And another thing that we can avoid, which we've had issues with in the past on ISS is very busy. There's lots of visiting vehicles, and visiting vehicles off gas. And so what we've had in the past when we have these exposure experiments, for example, EXPOSE, that's the name of the previous generation of exposure experiments external to the ISS, is you had contamination on the transparent windows where you would have samples sitting behind this window to get the exposure to solar radiation. But then all of a sudden you've got this deposition build up from the off-gassing of the visiting vehicles, and therefore not providing a clear experiment environment for these samples to get exposed to. So the gateway will be new, and it will have far less contamination, and we can be really smart, and we can take those lessons learned from ISS and really think about where we're going to place these experiments in terms of placing them further away from the visiting vehicles so that we don't encounter those issues again.
As we're recording, it's sort of approaching New Year, and 2022 is approaching. So I was just going to sort of finish off by first of all asking you, I mean, how has the past year been? Has the pandemic affected your work very much?
So time's a little bit of a blur, isn't it?
Yeah.
Yes. So it's been really interesting working in space research during a pandemic. In normal times, we would have had experiment testing going on prior to launches. We would have had dress rehearsals, like dry runs of experiment sequence tests, where we would carry out a full dress rehearsal of experiments as they would be performed in space in a dedicated test center, and everyone would be there together. But of course, with all of the lockdowns, we haven't been able to do that. So we've had to adapt like the rest of the world has, and we've done a pretty good job of that. And I hadn't previously ever had a Zoom call with a load of sample containers looking at me on a flow bench in a lab, but it happened. We managed to carry out these tests remotely with much scaled down staffing, and it was remarkable to see these tests being carried out just over webcam.
Yeah, I mean, science has to go on, doesn't it?
Absolutely. If science doesn't go on, we won't go on.
Absolutely, yeah. What about 2022? Do you sort of? I sort of find once the 1st of January hits, I sort of get this sense of it being a fresh start. Do you get that, or are you looking forward to 2022 and bringing like a new year of prospects?
I am looking forward to 2022. But in terms of space research, I don't think there's ever such thing as a fresh start. There's always this continual building upon heritage and lessons learned of previous experiments and looking to the next thing. Science is the process of building on what we already know to therefore go forward and answer the questions to what we don't know. So the next generation of experiments are coming up. So they are still in the planning. things have taken longer than anticipated, and some of that's down to the pandemic. But we have some really exciting experiments planned for low Earth orbit on the International Space Station. We have the next generation of biofilms going up. Now, biofilms, the experiment I spoke about a few moments ago, was actually distributed over 3 flights. The first flight has already gone, and the second one is coming up, I believe, February or March. And the reason for doing that is to produce the good science, we need a large amount of replicates. Anybody in a lab will tell you that the more data you have, the better. So we'll have the second flight of biofilms coming up, and that will test even more of these different surfaces, so copper, brass, and stainless steel in the space environment to see how the bacteria fares on those. And then in addition to that, we are still planning the next generation of external exposure experiments. I mentioned EXPOSE earlier. That was the first generation. Now the second generation will be the new exobiology facility. That will go on a platform called Bartolomeo on the outside of the Columbus module of the ISS. And that is, again, a series of biological exposure experiments. But for the very first time, we will have in situ measurement capabilities, which means that scientists don't have to depend on getting their samples back from space before they do their analyses. No, they can do it in almost near real time with data downloads. So that's really exciting.
Yeah, I love hearing about the sort of prospect for future research and missions. It's always really exciting, and it's always really encouraging to just hear about all the future prospects for scientific research, especially in the space arena. So I wish you all the best with that for 2022, and just want to say thanks again for coming on the podcast. And sure, maybe we'll speak again next year when some of these experiments are properly underway.
Yes, thank you for having me, and Happy New Year.